we're going to pick up where we left off on Tuesday. And so on Tuesday we learned how to do Lewis structures. And then at the very end, I said that today we're going to learn about shapes. So we're going to take those Lewis structures, which are in 2 dimensions, and we're going to turn them into 3-dimensional structures. And so we said that the shape of the molecule is very important. So it's important that we learn how to predict the shape, because the shape is going to determine the function of the molecule. And so we have a process that we go through, and it all starts with Lewis structures. When you want to find one of these shapes, you have to make the Lewis structure first. So, what can seem like a really simple question is what is the molecular shape or structure of this molecule is going to be multiple big steps. And you're going to have to do all of the steps to get there. In the process that we use to go from the Lewis structure to the shape is called this VSEPR theory. Most people just say VSEPR even though the S comes before the E. It's really hard to say VSEPR. And so we're going to use this, and the whole thing is based off the fact that since all electrons are negatively charged, they're going to repel each other. And since they're going to repel each other, they're going to get as far away from each other as possible, which means that the other atoms that are stuck to those electrons, the 2 atoms that the electrons are being shared by, if you have multiple atoms around your center atom, those outside atoms are going to get as far away from each other as possible. They're not going to be what's guiding where they go, but the electrons in their bonds are. So the electrons in this bond over here are going to want to be as far away as from this bond over here as they can be. When we start to make this shape, we're going to have an intermediate step that we have to go through. We're going to have the Lewis structure. We're going to end up at the molecular shape. In between, we have to go through what we call the parent structure. And the parent structure is going to be based on what I call the number of things that are attached to the center atom in our Lewis structure. And a thing can be either a single bond, a double bond, a triple bond, or an electron pair that's not part of a bond. And any of these four things count as one thing. A triple bond is one thing, and a single bond is also one thing. So what I want to do, actually I'm going to have to turn the lights on, is we're going to think through, in 3 dimensions, how we can arrange atoms around a center atom in such a way that they get as far away from each other as possible. So I have here a center atom. And then I have 2 bonded atoms that I need to stick on this atom. How are these 2 going to be arranged in relation to each other so that they are as far apart from each other as possible?
Opposite sides.
Opposite sides. So if we have 2 things, that's really easy. They're opposite each other, and so it ends up looking like that. Okay? So this is what we call a linear parent structure. I think these names are going to be on the next slide, but I don't want to put it up yet. So that's our linear parent structure. What if we have 3 things? Imagine I have 3 things that I need to put around my center atom. Just want to open all the way on the end there. I'm going to draw on the board. So if you want to arrange these 3 atoms around my center atom and spread them out as far as possible, how are you going to do it?
Triangle.
A triangle, right? Whether it be You want to think of it as a triangle, or a peace symbol, or a Mercedes-Benz symbol, or whatever you want to think of it as. It's going to look like that. These three atoms are as far apart from each other as they can possibly be. 3 is also pretty easy. You all immediately pictured that, right? The hard one is 4. If I want to add a fourth to this, and they still need to be as far away from each other as possible, what do you think it's going to look like? Right. It's not going to be like a cross or a plus sign because we're in 3 dimensions. If we were in 2 dimensions, then you would do a center atom and you would go like that. Those 4 are as far away from each other as they can be. But we don't have to limit ourselves to 2 dimensions. We have 3 dimensions. And if you work it out, what it actually ends up looking like is this. So you have 3 of them that if you look at them like that, it's still that peace sign shape, right? But they're angled down a little bit, whereas here they were all flat. So we essentially take that, bend the 3 down a little bit, and then add a 4th one sticking straight up. And if you take this, it actually, no matter how you turn it, it always looks exactly the same, right? All of these angles between these atoms are the same. And so if you have 4 atoms that are attached to the center and they're all the same, it literally doesn't matter how you hold this, it looks identical, okay? And so that is what these look like if you have 2, 3, and 4 things attached to your center atom. These are our 4 parent structures. This one's linear. This one is going to be called trigonal planar. It's trigonal because there's 3, and it's planar because we say they're all in the same plane. A plane is a line of symmetry. You just draw a line straight through it, and they're all in the same plane. This one is going to be called tetrahedral. Tetra meaning 4, hedral, I don't know. Tetrahedral, okay? So we got tetrahedral, trigonal planar, and linear. And so here we've taken pretty much the same thing, but with balloons, and you can see them again. That is how we're going to maximize the distance between our things. And so, coming back to our tetrahedral, this is methane. Methane is natural gas. That's what we burn in our Bunsen burners. And methane is CH4. There's a carbon in the middle, and then 4 hydrogens around them. The bond angles between these bonds are 109.5. That's a number you need to know, and it's not a number you're going to be able to figure out on an exam based on geometry unless you're some sort of math genius, in which case you should probably be in a higher level chemistry class. Okay? 109.5 is essentially a random number. If we come back to our linear one though, this is not a random number. This one is something, if you didn't memorize it, you could figure it out. Well, what do you think is the bond angle between these 2 atoms? 180. Because it's 360 the whole way around, and so it's half and half. There's 180. What's the bond angle on this one? What's 1/3 of 360? 120. So these are all 120. And so, in my mind, if somebody asks me what's the bond angle in a linear structure, I think, well, it's 360 divided by 2 is 180. If somebody asks me bond angle in trigonal planar, I go 360 divided by 3 is 120. I just think about it. But if somebody asks me this one, I better hope I memorized it. It's 109.5. So these are our three parent structures. We have linear, trigonal planar, tetrahedral with 180, 120, and 109.5 degree bond angles. Those are our parent structures. Remember, those are just the intermediate structure that we're going to go through between our Lewis structure and our molecular shape. But you have to go through this. You cannot go straight from Lewis structure to our molecular shape. So, I always have trouble with people not counting the things on their center atom, or not remembering how to count the things on their center atom. So let's look at these. On NH3, you have a nitrogen in the middle and 3 hydrogens going around. Okay? How many things are on that nitrogen?
3. 4.
You don't necessarily know, do you? Because think about what we said were things. We said single bonds, double bonds, triple bonds, and also lone pairs. And so looking at that, we know that there are 3 single bonded hydrogens. But we don't know whether there is a lone pair or not. And so we have to do the Lewis structure. You cannot do this without figuring out the Lewis structure. So how many valence electrons do we have to work with? Nitrogen has 5, so there's 5, 6, 7, 8. I've got 8. I'll put my first 6 in are easy. Where do my last 2 want to go? Put them right here. So now looking at that, how many things are on my center atom?
4.
There's 4. There's 3 single bonds and a lone pair. They all count the same. They are all one thing. So there are 4 things on that nitrogen. What's my parent structure of ammonia? It was this one. What was this one? Tetrahedral. 4 things is tetrahedral. Carbon dioxide is one that we did in class on Tuesday, so I'm just going to put it up here. How many things are on my center atom? 2. A double bond counts as one thing. Even a triple bond counts as one thing. So we have 1, 2 things. What is the parent structure?
Linear.
It's linear. Looks like that. What about SO2? SO2 is another one that we did in class. SO. How many things are on my center atom? 3. A single bond, a double bond, and a lone pair. What is my parent structure? Trigonal planar. There are 3 things. Even though one of them is a lone pair, it still counts. We have 3 things. It is trigonal planar like this. And let's do water. Water is not one we did in class. So how let's not use that marker. Water, we've got an oxygen and 2 hydrogens. Remember I said oxygen normally isn't in the middle, but in this case all we have is oxygen and hydrogen, and I said neither of them are in the middle usually. And so one of them has to be. Hydrogen literally cannot be in the middle because it can only form 1 bond. And so for water, oxygen's in the middle. How many valence electrons do I have? 8. Oxygen has 6, each hydrogen has 1. So I'll put them in there. Where do the other 4 need to go?
You have 2 lone pairs on the
Yeah, like that. So how many things are on my center atom?
4.
4. I have 2 single bonds and 2 lone pairs. Even though there are only 2 atoms attached to my center atom, I still have 4 things. It is still a tetrahedral parent structure. It is still this parent structure. Now that we have our parent structure, we can move on to our molecular shapes. So that is our water, right? And it's drawn in a tetrahedral shape, where 2 of them are hydrogens, 2 of them are lone pairs. What we're going to do when we go from the parent structure to the shape is we are going to imagine those lone pairs, those lone electrons, are not even there, and just picture what would be left if we erased the electrons. So let's take this, and let's erase 2 of our things. Now it looks like that. But that is not tetrahedral. Tetrahedral is with all 4 things. So this is going to have its own name. Does anybody remember, has anybody ever heard what the shape of a water molecule is? Bent. Water molecule is called bent, and it's bent because it looks similar to the linear one, right? Because there's still 2 things, but instead of being linear, it's bent. It looks like if I took this and I bent it. And so the water molecule is bent. If you take the tetrahedral and you pluck off 2 lone pairs, it becomes bent. So that is what we've gone through. On the next 2 slides, 2 slides? Yeah, 2. Next 2 slides is a table of all of the different possible molecular shapes. This is something you're going to have to memorize. Okay, you're not going to have this table, although it is not that hard once we get through it. And so the way it's organized is up here we have what they're saying is the general formula. Okay, and so that's the X there is the number of bonded atoms. Not lone pairs, but bonded atoms. And then up here we have the parent structure. So for our parent structure linear, this is the only possibility. You can't have a lone pair here, because if you have a lone pair, then it's just that. And that's not a center atom molecule. Okay? Everything that we do is going to have at least 2 bonded atoms. The question is how many lone pairs are there also. So for our linear parent structure, there is only one possibility, and so the molecular shape is linear. So the molecular shape is the same as the parent structure, and that is linear. If we go on to trigonal planar, now we have 3. And if all 3 of them are bonded atoms, we don't erase anything, we don't pluck anything off. So our molecular shape is this, and we already have a name for this. This is trigonal planar. And so the molecular shape name of this is trigonal planar. If you don't erase anything, the molecular shape name is the same as the parent structure name. But now, because we have 3, we only need a minimum of 2, so we can pluck one off. Now, I've got 2. What does that look like to you? It looks just like our water did, right? Here's our water. Here is what we just made from our trigonal planar. They look very similar, and so they're both called bent. What gets people is that there is actually a difference between them. The bond angles are different. if I hold them up next to each other, you might be able to see. It's very, very slight, but there is a slight bond angle difference between them. The bond angle is going to be determined by the parent structure. Okay? If you have a molecular shape that is the same as the parent structure, the bond angles in the shape are the same as the parent structure. So for our linear, it's still 180. If we have all three things, it's still 120. And if we have all four things on our tetrahedral, we are going to have 109.5. But as soon as you pluck something off, unfortunately that bond angle is going to change a little bit. If you have something, say you'd have either this one or this one, as soon as you pluck off one, or you pluck off one or two, it goes from whatever it was before to 107 degrees. That's a number you're going to need to know.
No matter what.
If you pluck one off, it goes to 107. And the reason for that, and the reason is not something you need to know, but if it helps you grasp the concept, is because when you pluck those off, the electrons are still there. You're just ignoring them because electrons are so small you can't see them. But in reality, you have the lone pairs that are there. And lone pairs have a negative charge because they're electrons. But here you have the negative charge from the electrons and also usually positive charge from the nucleus here, which kind of offsets the negativeness here. But once you only have lone pairs, the negative here is stronger than the negative down here, which causes everything to fold down a little bit to get further away from these. Again, that's not an explanation you need to know, but that is why when you pluck those atoms off, the bond angle is going to change. Okay? So there will be plenty of examples, because that's always something people forget. So there will be plenty of examples of bond angles where you pluck something off in the homework and quizzes and things like that. So now we've talked about the linear and the trigonal planar. So trigonal planar, we said if they're all atoms, we have still trigonal planar. We pluck one off, it's bent. Let's go to our tetrahedral. If we have tetrahedral, if we have tetrahedral, there are multiple possibilities. Because we can have four atoms bonded. That's this one here, AX4, with four bonded atoms, 0 lone pairs. We didn't take anything off, so it's still tetrahedral. It's called tetrahedral, and it has the bond angle of a tetrahedral parent structure, 109.5. If I pluck one off, this is now something new. This is a shape we haven't had anywhere else. This is called trigonal pyramidal, as opposed to trigonal planar. They both have three things, so they're trigonal, but that one is planar. Everything's in the same plane. This is pyramidal because it looks like a pyramid. So keep in mind that if you have only three things, and they're all atoms, it's trigonal planar. But if you start with tetrahedral and pluck one off, you have trigonal pyramidal. And if you take two of them off, now we're down to our bent again. Is that the last slide? No. Okay. So, we now have to put all of this together. This is the type of problem you would see on a quiz or an exam. Okay? All we're given is a formula. What is the shape of the nitrite ion? Okay? So let's count how many valence electrons are in there. We haven't dealt with an ion before, so there's a charge on there that we'll have to come to terms with. But let's just ignore the charge right now and count how many valence electrons there are in NO2. Nitrogen has 5. How many does an oxygen have? 6. So what does that come to? 17. But because it's an ion, it has a negative charge. Negative charge means it gained an electron. So now it has 18. So we have 18 to work with. In NO2, we're going to have nitrogen, 2 oxygens. I'll put the first two pairs in. Where are the rest of them go? Start out here. So that's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16.
Then you have a lone pair on the end.
17, 18. Is that finished? No. Nitrogen's only got 6. So what do you want to do?
Double bond.
Let's make a double bond. Now is everything happy? This oxygen only has 1 bond, but it's going to have to stick with it because there's nothing else we can do. If we make a double bond here, the nitrogen's going to have more than 8. And so that's the best we can do. Because this has a charge, we have to indicate that, and we put the whole thing in brackets to put a charge like that. So that's saying the charge is on whatever's in the brackets. And that charge is not on any specific atom in there, it's just as a whole, it has a negative charge. So we drew our Lewis structure. After we draw our Lewis structure, what's our next step? Parent structure. What's the parent structure of our center atom? How many things are on my center atom? 3. There's a single bond, a double bond, and a lone pair. That's 3 things. And so the parent structure is trigonal planar. And so what we're going to do is we are going to draw it, and we're going to draw everything that's attached to it, and we're going to draw it, making it look trigonal planar. And so I'm going to do, that. So that is a drawing of my parent structure, but that is never going to be an answer for a question. Okay, this is just what we have to go through to get to our answer. Now all I have to do, though, is erase my lone pair. That is my shape. And so, number 1, it asks, what is the bond angle?
107.
107. We started like this at 120, but we plucked one off, so now it's 107. What is the name of that shape? Bent. It is bent. What we went through. Okay. So now that we've drawn molecular shape, we have to add one more thing, one more conclusion that we can draw from our shape. And that is whether our molecules are polar. A polar molecule is going to be asymmetric. And it has to do with the same as the bond polarity. Remember we said we had nonpolar covalent bonds and polar covalent bonds. Nonpolar covalent bonds were between two atoms of the same element or carbon-hydrogen. Polar covalent bonds were a bond between any two different elements. If you had two different elements, as long as they weren't carbon-hydrogen, they were going to be polar. If we have a diatomic molecule, meaning there's just two atoms, looks like that, the molecule polarity is going to be the same as the bond polarity, because there's only one bond, and so if the bond is polar, the molecule is polar. Where it gets more complicated is with atom molecules that are more than diatomic. They're polyatomic. For these, we have to use a little bit of logic and thinking about what these actually will look like. If we have a polyatomic molecule that is all one element, or made up only of carbon and hydrogen, that means that all of the bonds are going to be nonpolar. If all of the bonds, and I mean all of them, are nonpolar, the molecule itself will be nonpolar. If you have a molecule made up of all one element, or just mixture of carbon and hydrogen, it will be nonpolar. That one's pretty simple also. But if we have a polyatomic molecule made up of different elements, in some cases it will be polar, in some cases it will be nonpolar. And the way to figure it out is to think if the polarity of the bonds will cancel each other out. And this is a concept that people struggle with sometimes. How many people have taken physics before? One. Okay, that's not going to help much. So in physics, we learn about forces and vectors. And so we say, imagine a tug of war, okay? You have two people pulling on a rope. Imagine there's one person in the middle. That's going to be our center atom. And there's two groups pulling on either arm. If they both pull with the same strength, I'm not going to move. Okay? That's essentially what's happening in our non-polar atom. This is two different elements. These are two polar bonds. But they're directly opposite of each other. They're directly opposite of each other. And they're equal. It's a red with a white. And so these two bonds cancel each other out. And even though the bonds are polar, the molecule is nonpolar. If I take a green one, these two bonds are not equivalent to each other. Even though they're opposite of each other, they're not equal to each other, and so they don't cancel out. Here we have a center atom with two same atoms, two green ones. These two bonds are equivalent to each other, but they're not directly opposite of each other. And so they don't cancel out. Where it gets a little harder to visualize is if we have three of them. This actually does cancel out. In this case, let's draw a line this way and see if it's symmetrical. If I draw it this way, I have a green one on the left and a green one on the right, and they're both pointing down the same. And actually, one is pointing straight up, and two of them are pointing kind of down. So the down from these two together is equivalent to the up of the one. Okay? So that is how you want to visualize that. Same thing goes if we have, oh, that's not going to work. If we have 4 on our tetrahedral, and all 4 are the same, that is going to be non-polar. As soon as we take one off, though, it's polar. We have 3 of them on the bottom and none of them on the top. So a way we can simplify this, if the molecular shape is the same as the parent structure and all of the bonded atoms are the same element, it's nonpolar. So essentially what I just described is that in this, and also are linear. So these cancel out. If they're all the same element, if these 4 are the same element, they will cancel out. If these 3 are all the same element, they will cancel out. And if these 2 are the same element, they will cancel out. But as soon as you take one of these 2 and one of the outside atoms is different from the rest, it immediately becomes polar. There's no way for it to be nonpolar at that point. If I take off one of these greens and put on a white, I have 2 greens on that side and a white on that side. That is not symmetrical. It is not going to cancel out. If I pluck one off, if one of them is a lone pair, there's no way it can be nonpolar. The only way it's going to be nonpolar is if they are all atoms going around it and all of those atoms are the same element. As soon as you replace one with a different element, as soon as you pluck one off because it's a lone pair, it is polar. So this is what we're looking at, but in drawings. So this is how we will draw polarity of a bond. Okay? And so what we have here is an arrow, and on one end of the arrow is a positive sign. Do you see that positive sign on the end of the arrow? That is going to denote the positive end of that bond. The arrow points towards the negative end. How do we figure out which end is the positive and which one is the negative, though? Because it's covalent bonds, they're all nonmetals, and so we have no ions here. They're all nonmetals. Remember electronegativity? That was in the video. We briefly talked about it, though. Whichever element is closer to fluorine will be the negative one. So here's sulfur and oxygen. Oxygen is closer to fluorine, and so the arrow points to it. The one that is closer to fluorine will be negative. And the arrow points to it, and you put a plus sign on the other end. So this is our trigonal planar. We have 3 polar bonds, but they cancel out. This is carbon tetrachloride. There are 4 polar bonds here, but they all cancel out. And you notice how this was drawn here. If we're drawing linear or trigonal planar on a board, it's okay, because they are planar. I can take this and put it like that. It is planar, and so I can draw it on the board, and it will look on the board just as good as it does here. But that is not planar. And so I can't really draw this very well on the board. Yes, I can go like that. That's the best that I can do. Okay? But that doesn't really tell what's going on. So we have these dashed lines in the solid wedges. Okay? A solid wedge means that that bond is sticking out from the paper. It's sticking out towards you. It's out from the board. The dashed wedge means it's going into the board. It's going into the paper or away from you. And so with that tetrahedral one, essentially what we have is this. It's been arranged so that these two are in line with the board. This one is sticking out at you, that's this one, and this one is sticking away from you, that's that one. Okay? So if you're drawing something that is 3 dimensions, please use the wedges, whether they're solid or dashed. Okay? So that will be for tetrahedral. You'll have 2 of them that are just lines, and one that is out, one that is in. If you have trigonal pyramidal, what you're going to do is you're going to take off one of the lines, and so you're still going to have, let's get rid of this, you're still going to have one in and one out. So that's our trigonal pyramidal. But once I pluck this one off, I can turn this however I want. And so I would suggest turning it so that it's in one plane. So then you don't need wedges anymore. So the only time you need wedges is if you have tetrahedral or trigonal pyramidal. Anything other than that, you don't need to worry about. Because anything other than that, you can lay flat on your piece of paper. So let's look at these. There are 3 molecules up there. So we started with the carbon tetrachloride. We started with that, and we're going to replace the one on the bottom. We're going to replace some of them with hydrogens. So the one on top, we replaced one with a hydrogen. Is that polar or nonpolar?
Polar.
It's polar. There's several ways we can tell. Number 1, it's not symmetrical. If you can draw a line through that center atom, and it's not a mirror image on both sides, it's polar. Okay? And so, if you can draw that line however you want, if there is one line, even if there's 50 of them where it is a mirror image, if you can find one line where it is not a mirror image, it is polar. So if we draw a line like this, it is not a mirror image. We have 3 green ones on the bottom, a white one on top. There's also the simplified rule that we learned. Yes, there are 4 atoms, but they're not all the same element. And so immediately they are polar. It is polar. What about this one, polar or nonpolar? It's polar. Again, if we draw a line like this, we have a green one over here, some white ones over there. It's not symmetrical. And also, all 4 atoms are not the same element. Same thing down here where it's 2 and 2. We can have green ones on one side, white ones on one side. That's not symmetrical. And also, they're not all the same element, depending on however you want to look at it. Polar or nonpolar? Polar. You can draw a line like that, and it's not a mirror image. Even though you can draw a line like that, and it is, if you can find one line that you can draw, it's going to be polar. What about this one? Polar. If I draw a line like this, I have green ones on the bottom, white ones on top. What about C? C is a little hard to see what's going on. And so what you're looking at is that. It's polar. These stick down a little bit. And so we have 3 white ones on the bottom, none on top. Even though if you look at it that way, it is symmetrical. It's 3-way symmetrical. If you look at it that way, it's not. All the white ones are on the bottom. D, you're looking at this. This one's nonpolar. See the difference? And this one All the white ones are on the bottom, there's none on top. On this one, if you draw a line cutting through like that, you're going to cut the green ones in half. In each, a half of the green one's going to be on top, half the green one's going to be on the bottom. If you look at it this way, it's going to be three-way symmetrical. Okay? If I cut it like this, I'm going to have 1.5, 1.5. And it's still a mirror image. And so this, D, is non-polar. Okay? So you're going to have to do examples of these to get comfortable with it. And that is exactly what we're doing in lab today. So if you brought your lab experiment, if you have it printed out, why don't you get that out? I'm also going to put it up here. So you're going to be working with these kits. So they're on your benches in there. And so you're going to go through and you're going to have to find the molecular shape of a number of different molecules. So if you printed this one is kind of a whopper. You have to print like a whole tree's worth. But most of it is instructions. And we just went over the instructions. Okay? So we're going to scroll all the way down to the main part. This data table here. If you follow the rules we just went over, all you need from this lab is the data table portion. Okay? Actually, let me get mine out. I just need to find my copy. Because I don't make you do all of them, and so I just need to look up which ones I normally make you do. So if you look at this table, what it does is it gives you a formula, asks you to draw the Lewis structure, asks you to predict the molecular geometry. That's the name of the shape. Whether it be linear, trigonal planar, tetrahedral, bent, trigonal pyramidal, whatever the name of that is going to be. What is the bond angle? And then you make it with your kit and then draw the best that you can. Okay? For a lot of you, it's going to be horrible. That's okay. It's probably better than I would draw it. Draw it the best that you can. Making it with the kit and being able to predict the geometry, the name, and the angle is the important part. Drawing what you made isn't all that important. So what I want you to do is look at your table and cross out C2H4. You don't need to do C2H4. You don't need to do C2H2Cl2. You also don't need to do BF3. Okay? So the other ones, there are 3, 6, 7 that you need to do. On the last page, there's another table. It's the same formulas, and it just asks, is it polar or non-polar? So for the ones that you actually made models of, those 7, go through and mark whether they're polar or non-polar. For the ones that you didn't make the model of, don't worry about them. Okay? That is the lab for today. There is no post-lab. So you don't have a post-lab for this week. Okay? So let's go over next door. If you want to just jump right in, you're welcome to. I'll unlock the door for you.
Do we need to allow